Hello, welcome everyone to today's RAVENNA webinar. This will be the final webinar of the RAVENNA remote session series, where we are focusing on remote productions. We have heard in the past webinars on the basics of AES67 over wide area networks from Niklas Stürmel from Merging Technologies. Daniel Bolt from Mindwork was telling us how we can deal with timing and synchronization in wide area networks. Luca Giaroli from Direct Out was presenting the Lockdown Rock project, which is about remote recording. Dirk Sikora from Lavo was introducing us to Real Life project in sports and news remote production. And today we will take it to the cloud with a live intercontinental production demo under the lead of Ross Video. My name is Andreas Hildebrand. I'm working for ALC Networks out of Munich, and we are developing and maintaining the RAVENNA IP media networking technology, which is a licensing-free open technology approach, which is also fully AES67 and ST2110 compliant. So today's presenters will be Bill Runopoulos from Ross Video. Bill is business development manager for OEM and partnerships, and Angelo Santos, he's solutions architect. In both are working out of Ottawa, I guess, Canada. So welcome, Bill and Angelo.
Thanks, Andreas.
Yep. And further on the line will be today's guest, Niklas Stürmel from Merging Technology and Claudio Becker-Voss from Direct Out in Germany. So Claudio is joining us from South Tyrol today. He will join in later and participate in this demonstration today. So what are we going to see today? Well, we will have a global AES67 over wide area networking demonstration, including 2 continents, 4 sites on these continents, and with 3 participating RAVENNA partners. So we will send RAVENNA AES67 live streams back and forth between the labs of Ross Video in Canada and Merging and Direct Out residing here in Europe, in Germany and in Switzerland and in France. We will be using the public internet and a public cloud infrastructure. And of course, we'll discuss the demo setup, the technologies required, the equipment which is being used, and we will discuss future consideration to make practical use of the capability in real applications. All right, so without further ado, I will hand it over to Bill Runopoulos from Ross. Good morning, Bill. It's your turn now.
Good morning, Andreas. I want to start with an overview of today's intercontinental remote production demo. A lot of effort, planning, and coordination has gone into it. It involves equipment, as Andreas mentioned, from 3 RAVENNA partners across 4 different sites over 2 continents, and leverages the public cloud infrastructure from Amazon Web Services. I know you're all anxious to jump right into the demo. Before we do that, we would like to review why we are doing this and provide some background on the challenges. This will be followed by a quick description of the setup and equipment at each site. We will then go to the demo and give you a link to a web page where you'll see the volume unit meters and have the ability to listen to the live audio streams. Afterwards, we will discuss what we learned, outline topics for future study, and wrap up with Q&A. Let's start with the why. We want to understand if we could send RAVENNA AES67 traffic over the public infrastructure and the cloud. The basic question is, can we do it? And can we do it across long distances? Even if we can, would we be able to listen to something resembling audio? Would it be good quality? It is one thing for a single company to do it with their own equipment, like we experimented with at Ross in North America, but could we operate with equipment from other companies, which is the whole point behind RAVENNA and AES67? Finally, how could we do it? What challenges would we face? First, let's have a little bit of background. RAVENNA and AES67 use IP, but they were designed with the local area networks in mind that are synchronized to precision time protocol. Packet loss is not an issue in the LAN and wasn't considered as part of RAVENNA or the AS67 standard. Having said that, RAVENNA and AS67 have been proven and are being used in WAN applications across some private networks, even though WAN applications were not contemplated by the standards. Private dedicated networks, whether owned or leased, are architected well and come with performance guarantees. This is not the case for public networks. Public networks are the equivalent of the Wild West. You can't control them. They are congested and unpredictable. They suffer from packet loss due to link failures and have large, sometimes dramatic delays due to packet retransmissions. The public network is a very harsh environment for RAVENNA and AS67. Let's take a look at the three main challenges. Increased latency and packet jitter is definitely a problem. Drop packets, how do we deal with them? And timing and synchronization, which is always a challenge, but more so in this situation. Now let's go into a bit more detail on each of these. The increased latency and packet jitter would normally be a massive challenge. RAVENNA receivers handle this by design with large receiver buffers. These, along with other techniques leveraging those buffers, can compensate for the added delay. RAVENNA requires receiver buffers to handle at least 20 milliseconds of latency or delay, while AS67 specifies a minimum of 3 milliseconds but recommends 20. Most well-designed RAVENNA and AS67 solutions, like all the equipment used in this demo, come with even larger buffers and can handle much more latency. An AS67 standard working group has been formed that is focused on the use of AS67 in WAN applications. And one of its key recommendations is to increase the minimum buffer size in AS67 solutions. In summary, the increased latency of the public network is not an issue for RAVENNA. Next challenge, packet loss. This is an important one. RAVENNA and AS67 are not designed to work with drop packets. Fortunately, there are other transport protocols that are architected to deal with drop packets without introducing a lot of extra latency. These were mainly designed for video, but can work with audio. Example of the most popular ones are SRT, Zixi, and lately RIST. In this demo, we solve packet loss by encapsulating RAVENNA traffic within SRT. Some may cry foul here that we are not actually transporting AS67 if we're using SRT. But you can think of SRT as just a wrapper, and in no way does it alter AS67 packets. The audio is still transported end-to-end as AS67. The final but significant challenge is timing and synchronization, which is key to RAVENNA and AS67. We start by having a separate PTP grandmaster at each site that is synchronized to GPS. All the equipment at each location is locked to PTP locally. No PTP packets are sent across the WAN or through the cloud. This is not currently practical as packet jitter is too high. Instead, we leverage AWS's time sync service, which uses Crony, which is also locked to GPS. Since the PTP GM at each location and AWS Crony are GPS locked, we can maintain synchronization across the WAN. This is how we solve this problem. Now, let's take a look at the equipment and setup at each site. At Ross Labs in Ottawa, Canada, we are generating the AS67 sources from our SoftGear platform. SoftGear is a future-facing signal processing platform architected to efficiently acquire, process, manage, and distribute content, offering audio, video, and metadata microservices on a commercial off-the-shelf platform. SoftGear's modern OS-level virtualization enables easy scaling, migration, and redundancy, giving you the ultimate flexibility in solution deployment. on-premise today or in public or private cloud tomorrow. It delivers best-of-breed processing through ROS and third-party microservices, so you can benefit from world-class signal processing. SoftGear allows you to easily adapt to changing workflow requirements to address rapidly evolving environments. Although we are only focused on transport today, in preparing for this demo, we did an experiment at ROS, which also included processing in the cloud by running Nielsen audio watermarking encoding at AWS while sending AS67 streams back to our lab. At ROS, we are also receiving streams in this demo with our IGI platform. IGI AS16.16 is a compact yet full-featured, broadly interoperable and flexible live audio over IP bridge, easily deployed anywhere without compromising on channel density. It allows you to handle 16 AS3 channels in and out via DB25 connectors. Its felt form takes up little room, important when space is at a premium, enabling you to have the freedom and flexibility to bridge your AS3 audio to IP wherever you need it, whether it is in a studio, truck, on stage, or in a fly pack. IGI effortlessly adapts to your environment with broadcast-grade robustness, power over Ethernet, and hitless 2022-7 audio interfacing, while it is also silent for in-studio use. As we like to say, don't let bulky equipment get in your way, get IGI, and get groovy. Now I'm going to turn it over to my esteemed colleague, Angelo, to review the ROS setup at our Ottawa lab.
All right, thanks, Bill. So now we're starting to talk a little bit more details on each setup on each vendor. On our side, as Bill mentioned, we generating the stream, which is a true channel stream from a SoftGear. It's basically a looping some music, and you're gonna hear that on the live presentation. So basically, we have our internal ROS network, and we generate this multicast stream to a SRT gateway that encapsulates and send it to the AES server in Virginia. The other way around, we take the streams from the merge and direct out through the SRG gateway, and then we receive on the AES1616. That's the listener side. So as Bill mentioned also, we have to make sure those equipments are all locked, PTP locked to GPS capable PTP Grandmaster. In our case, we're using the Tektronix SPG 8000A. Bill, can you go to the next slide, please? So you can see the details here, but basically on the left side, you see that we're using our dashboard to create the stream on the SoftGear device. And on the right side is the IGI, and you can make the connection. And of course, you have to adapt the big network delay to compensate for the around 500 millisecond delay. We're gonna see in the demo. So this is just a snapshot. Of course, later, if you guys wanted to see, not in this presentation, but in another occasion, I can demonstrate that. Okay, Bill, can you go to the next slide?
So now we're going to hand it over to Nicholas from merging.
Thank you, Bill. Yeah, so with merging, we also have a couple of devices that are connected to this SRT network through the Lausanne and Grenoble, which is my home testing network. So the first device is the merging audio device, which is an Azure driver that basically acts as an audio infrastructure within the computer, so you can route signals, different multiple Azure hosts, and of course it integrates very well with merging devices, but it's also Ravenna and AES67 compliant. It's VM ready, and we have some big customers using it right now with VM and MOS. It also does ST2110 and 2022-7. And then we have the merging interface, which is a complicated interface with analog input and output, GPIO, MIDI, which has been tested with SIMT ST2110, and which does OSC, Heinemann, of course, Ravenna, and MOS. So the setup is that we have this big local area network, which is actually over a VPN between Grenoble and Lausanne. And on those networks, we have some computers with the MAD driver who are playing audio, and the Anubis who is receiving the audio from the internet. So in the middle, you have the gateway, and I did a simple software to not only allow connection with SRT using the SRT live transmit from AVision, but also sharing the SDP and updating the SDP information with the chosen multicast address on the receiving side. And of course, all of this is streamed to a relay server, which is basically just SRT endpoints that allow us to do network address translation, firewall punching, and avoiding the need to do port forwarding on the client side. And we have a SonyFX Grandmaster, which is linked to GPS, which ensures that we still have the same clock as everybody else. And so in the setup, it's always the same. All the merging devices share the same user interface. It's on the Ravenna Advanced page, and the only thing that has to be set is the delay in samples that has to be done, put up to here 336 milliseconds to be able to receive the packets. So as Angelo said, if not in this presentation, but if later you want me to show you how we configure the device, we can, of course. And the device is configured in manual mode to input the SDP. That's it for merging.
Now we're going to hand it over to Claudio.
Yes, thank you. Yeah, I'm using in my place Prodigy MP, which is a multifunction processor with DSP capabilities. It's a modular device with analog MIG-line ADDAs, MADI interface, AES, and of course network interface. In this case, I use the RAV.io, which is a Ravenna board, full-fledged Ravenna implementation, ST2110 compliant with ST2022 redundancy support. And this package can be remotely controlled by a number of protocols. We support NMOS, Ember Plus, Heinemann, for instance. So it's a quite versatile box. And on the next slide, we can see how I put this together. As a Grandmaster, I used a little Raspberry Pi, which is connected to a GPS antenna. It's called PT Pi, and yeah, this is of course not a top-of-the-notch Grandmaster device, but for this purpose, it serves well, and I get at least GPS timestamps in my streams. Then inside of the Prodigy MP, we have the SRT gateway. So the Ravenna board streams out Ravenna stream, and then it's packed into an SRT stream, which goes out to the Amazon server in Frankfurt. And on the next slide, we can see the receiving side. Yeah, screenshots of the input buffering I had to apply to receive properly the the streams from Ottawa and also Lausanne. You can see the offsets are a bit different, the stream delays. It's around 460 milliseconds for Ottawa. The actually measured offset of samples was right below 20,000 samples. So I put a bit of extra for overshoots, but with these settings, I could receive properly the stream without any drops. And from Lausanne, it's about 333 milliseconds. So it's possible to receive those streams properly, although you need some buffering in the devices, and they need to be large enough to accommodate for this setup. Okay, so far from my side. Thank you, Bill.
Thanks, thanks, Claudio. And now I'm going to hand it back to Angelo.
Yes, since you talk about the individual setups, this is the overall, just to give you a big picture. You see that on the left side is the transmit side, and on the Ottawa side, let's say, on the right side is the European side. They're pretty much symmetrical. So this is just to show the overall demo. So you see on the left side that on the TX side, the A67 stream go through the SRT live transmit. The idea here was to use everything that is standard and available to build blocks on top of that. You see in future, there is a discussion on what we're gonna do next, right? So this is just to show overall the demo we have today. And you can see that we have synchronization on each end and on the cloud as well. The two servers in the AWS servers are connected to Virginia and Frankfurt. And between the sites and the cloud is SRT, as we spoke already. And you can see on the top is we generate the SDP file on the source, and we have to take that manually and create our receiver or destination. And as Claudio and Nicholas said, we have to manually adjust the network delay. We measure the delay, and then you adjust our buffer to avoid any problems with that. So this is the, let's say, the big picture of the presentation or the demo, and we can see maybe right now, Bill, can you go to the next slide? I think we can show the live presentation.
Yeah, here I'm going to hand it over for Nicholas to do an introduction on the demo webpage he put together.
Yeah. So in order to have a live demo that is fun for everybody, including for you, the viewers, I designed a web page that is actually in the relay. So the relay has a web server, and the SRT live transmits that are used for receiving and sending the SRT streams are actually also outputting the RAVENNA stream to the local loop of the device, which allows the server to receive the audio, just catch it on the fly, and stream it to you. So all the audio is analyzed. So you will see in the millisecond, in the white slot, the numbered millisecond, which is the delay between the stream and the real time. So basically, it's the transport time, or what we call the offset generally. And the audio you will hear is actually the 16-bit 48 kilohertz audio that is transmitted to you in real time, where real time with 1 second of buffer. So if you have a small internet connection, this may not work great. It requires at least 2 or 3 megabits of transfer speed. There's no encoding at place here. And of course, as you will see, when you click in on a city, you will listen to the audio from this CD. I think I went over everything. Then Bill, maybe you can show the demo.
Let's show the demo here. Let's take a second to switch. Okay, there it is on the screen.
So this is the demo, and one first thing, and we will talk about that in the conclusion. But you see the Lausanne and the Grenoble, they are actually kind of the same stream, but with different SRT delay, which is the time that SRT has to ask for a packet back if it is missing a packet. And you see that with only 140 milliseconds, we still lose some packets. Whereas when we put a lot of delay, it's much more stable. So this is one of the outcomes that we saw. And on those two streams that you can see, I will live just pause the audio. That is a paramix just playing, and you see that you get the audio out with flat VO meters and then back on again. So just to show you that it's actually a real demo.
I just have posted the URL, the live URL, so that people who are interested can now or after the webinar jump to that page and check it out for themselves. So sorry, Bill, go ahead.
Oh, no problem. I was just going to repeat the same thing. I mean, we have the URL there. You can go to this website. It'll be up. And you can click on the various cities and listen to the various audio streams. So this demo will be up.
Yeah, to hear the audio, you have to click on the name of the city.
And it's, yeah, right, like so. If you click on it, to change color, you'll hear the audio.
Get back to the presentation, and while the demo is still on, which I think was very, very interesting, of course, the question comes up, what particular lessons have we learned from this exercise, Bill? So can you introduce us to that particular topic?
Yeah, and I think this is an open forum for discussion. So we just captured a few things that we noticed during the presentation. So hopefully you had a chance to visit the website and play some audio. As mentioned, there will be, you can do this throughout the day. Now we'll review what we learned. First, the first important point is we can actually send Ravenna and AS67 over the public WAN. That's awesome. So that's great. The other aspect to it is the timing and synchronization. So it appears that local only PTP synchronization and AWS locked to GPS works just fine. So that's good. The packet loss, which we're very concerned about, can be managed via SRT. So that worked well. Connections were set up manually. Latency at significantly less than 1 second is, I believe, comment from the others, but is lower than what we expected, but still significant. To manage the increased latency, we had to manually tune the link offset at each site, and that was expected. But the deep buffers of the receivers were able to handle the network delay.
Yeah, so any further remarks, Claudio or Nicholas?
Not much. I mean, actually, this it was that simple to use SRT. During the first test, when Bill and Rogero came to me and said, "Okay, we want to use SRT. Here is the link, which is a GitHub repository." I just installed SRT and I was connected and exchanging stream in like 5 minutes. So it's really like a tunnel that ensures that you don't lose any packets. So of course you need to fine-tune the connection, and you will still lose packets because, well, the internet is a wide network, but it's really astonishing. And the demo you are seeing now, the demo you are seeing now has been running since last Tuesday, I think, without interruptions. So that's very stable and just based on the basic SRT. That is, I mean, we are not even beginning scratching the surface of what we can do with this technology. So it's very promising.
From my side, just one comment regarding the stream latency. Of course, this setup is not as performant as what we showed with the Lockdown Rock, where the aim was, or the goal was, to have musicians playing live on different locations. I think this is currently due to the SRT layer, which introduces too much delay to make that possible. So it's a different approach, and probably there's also space to tweak SRT left. Well, just to make it work and to have the possibility to exchange streams where latency is not such an issue, it's really simple to implement.
Yeah, so the whole, as we mentioned before, the whole idea was to use what was available already in terms of standard, and you can see that it's something simple to implement, and that we can build on that. SRT is one of the choices, but there are other options you can try later. The idea to use SRT because it was something very simple to set up, and you can do the demo and investigate the limitations and see what you can do. And overall, the RAVENNA streams were very good in terms of transmitting over the WAN.
Right, very good. Amazing that the synchronization works even across the cloud. And yeah, I mean, Claudio, the main difference, of course, was you were using public access, but then you have a virtual private network provided by your internet provider. And here in this example, in this exercise, we're using public infrastructures, you know, I mean, public network access and then just the public Amazon Web Services cloud. So totally different approaches to achieve whatever your particular goal is. Very interesting.
Here we are not using redundancy. We are using live kind of live reception check, where you check that you receive all the packets and you are asking the missing packets back. Of course, much of this latency is the delay budget that we allow the SRT layer to ask the packet back. If we lower this delay but use redundancy, as with ST22 2022-7, then it's always a trade-off. So you don't have any redundancy, then your delay gets higher, and when you start to introduce redundancy, then you can lower the delay up to the way where you could have the shortest delay.
Yeah, that directly leads into the question: what future considerations can we look at, Bill?
Yeah, I agree, and we'll jump to that. I just wanted to make one comment based on your comment, Andreas, is that this was a proof of concept demo that we put together relatively quickly, but the whole goal was we're going over, essentially, as we mentioned, a completely uncontrolled network. You know, so we had zero control over the transport across the cloud and all that. Obviously, in a real world situation, you know, you would try to make changes to try to engineer the network, so to cut down on delays and all that, as we mentioned. So let's go to the future considerations. First of all, as I said, proof of concept demo. We are very pleased with the results. It required, so a couple of things. It requires some expertise in fiddling with manual settings to get it to work. That's on our equipment. Again, we did not control the network. There are a few items for further study to make it more of a practical solution. A big one is, how do you transport timing or the clock through the cloud? I know a lot of people are looking at this, but that definitely currently remains a challenge and something for further study. Another aspect here is, instead of all these manual connections, it would be very valuable to be able to try using Ravenna registration and discovery over the cloud. You know, we use manual, we did this manually with SDP files, but it'd be great if we could automate this. Ease of use would be greatly enhanced if also the link offset could be handled automatically to compensate for the network delay instead of being manually tuned. As Nicholas mentioned, and actually Angela as well, to manage packet loss, it would be interesting to figure out if 2022-7 redundancy would work. I'm eager to try that just to see. And although SRT worked great, it would be good to experiment with RISC to compare performance. Where very certain RISC will work, it's just will it give us even better performance? That's supposed to be the promise of RISC. So I don't know, gentlemen, if you guys have some comments as well on future considerations.
I'm not sure about transporting the timing through the cloud. It's something that people are discussing all the time. The fact that we have a local time locked to GPS, and that worked really well. I'm not sure if something different than this will provide any benefit. Of course, we need to try other things, but this demo seems to prove a very interesting application with the local time.
Right, and we learned from Daniel Bolt a few webinars ago that if you're not involving the cloud but wide area network connections, there is a way of actually utilizing PTP over wide area network. And I don't know if that would apply to the cloud as well, maybe not yet, maybe later in the future. But what we have shown here is definitely that we have different options and ways to actually synchronize devices depending on the situation and you know, the requirements of the application. And yeah, I mean, timing errors are compensated by latency at the end. So if we don't have very, very exact time, let's say an offset of even a few hundred microseconds or even into the milliseconds range, we can compensate for that by adjusting the offsets in relation to that.
Yeah, I think what is most important is actually the advertisement and the signaling of the stream and being able to extend the Ravenna way of connecting beyond the local area network. So when we get to this, again, it's what remains, it's fiddling with the parameters and trying to find a better solution. But in terms of interoperability and compatibility within manufacturers, this is a definite item that will ease the life of our customers.
Yeah, just a final remark on that one. We have defined DNS-SD as the mechanisms for Ravenna advertisement, but as far as I know, very, very few Ravenna devices have actually built in full DNS-SD. Most of them are using MDNS, and MDNS actually doesn't travel very well across routed environment, particularly not the internet. But yeah, there are other mechanisms, and since Ravenna is open technology, you can use other mechanisms. For example, like suggested with NMOS or other protocols to let the announcements and the SDP files, you know, semi or full automatically be available at the various sites. Then actually that concludes the presentation part of today's session, and we'll jump directly in to our question and answer section. I bring in Roland, who is monitoring the questions which were coming in. I guess quite a lot of questions were coming in. So Roland, it's up to you to lead our way through them.
Yeah, guys, keep the answers short because there's a lot of questions. Amazing response. So lots of questions. I'm trying to decide the best order to do this in. First question: what services were running on AWS, and did you consider alternatives?
So I can answer that. We have EC2 elastic computing instances running in Frankfurt actually, but I think it's the same for Claudio and Fangero. And I have a Tetra one, T3 one, micro or mini. I don't remember. And I did test other platform basically as long as you have the needed resources to do the streaming, which are not that much for our single stream. It's working. So virtual machines. The short answer is virtual machines.
Yeah, Crony also is something that can be used if you want to do some processing in the cloud. And it's important to have Crony because that makes your processing also synchronized to GPS.
Okay. How much latency is added by using SRT?
That is a very good question.
That's a good question. I don't know if we looked at how much added latency there was.
So by default, the latency is 120 milliseconds, but it is best if it is 2.5 times the round trip time between the sender and the receiver, because the receiver will ask the packet back and you want it to be able to re-ask it. So ask it once and then ask it twice maybe. So if the ping between the sender and the receiver, for instance, if the ping is 100 milliseconds, the default parameter, which is 120 milliseconds of latency, will work, but it will work best with a latency of 250. So SRT doesn't really, as far as I know, SRT doesn't really auto-adjust to the round trip value.
Yeah, we measured about 120 milliseconds when we're doing our initial tests. But of course, you can adjust a little bit there. But this is the, let's say, the number you can have in mind.
Okay. And how was the connection to AWS? Is it a GRE channel or VPN?
It's pure internet.
Yeah, that's the whole goal, to do
nothing
special.
So SRT is using UDP, so unicast UDP, and it's two-way UDP because there's the discussion between the sender and the emitter. So this is the only thing I'm doing. UDP using the public IP of the elastic computing server.
So the SRT gateway is straight connected to a DSL connection, for instance.
Okay, understood. Another question here, which is a variation on a question I wanted to ask, actually. It's, can you comment on the AWS infrastructure, or what role it played in comparison to a generic transatlantic IP service? And really what I was going to ask is, if you could speak to Amazon and ask for changes, what would you ask them to do to make something like this work better?
Very good question. And well, the advantage we saw on the AWS is to connect the two servers. There are a bunch of things you can do to make it, let's say, a more robust and nice connection between the server. We tried to do some tests using involving Latin America, to be honest, for this demo. But we had some trouble, and the initial thing was to try to access the server in Virginia directly from Sao Paulo, and that was not a good idea. And so if we connect between the server between Virginia and the server, the AWS server in Sao Paulo, you get a very good result. So that's one advantage of using the AWS in this demo. We did not try other venues yet, but this is the thing that we saw right away using the AWS platform.
I think to add to Angelo's comments, another reason for choosing AWS is that there's a lot of applications running in the cloud today, and people are using it and trying to figure it out. And from our side, we'd also like to do processing in the cloud as opposed to just transport. So by leveraging it, you can do both. So that's another reason why we chose to do it that way.
Okay.
And on top of that, one thing I would like to ask Amazon actually is to lower the data fee. So let me explain that. When you have a server, it is designed so that you pay for the server, for the virtual machine, but you have to pay for the outgoing data as well. Or if you don't want to pay, you have to use the CDN, the Content Delivery Network, to serve the web pages. So here we are doing peer-to-peer, and we are outputting a lot of data out of the server directly. So this is the thing I don't like about Amazon, and this is typically provider-wise, because there's another provider in France, in Europe, and it is beginning to get data center in the US as well, which is OVH. And OVH has a completely different business model, which doesn't charge for outgoing data, for instance. So it really depends on the expected performances and traffic that you get for your system, or that you want for your system, and the choosing is there. But of course, Amazon has the advantage of having a lot of more data centers, so you can really get the shortest ping by choosing the data center closer to you, and this has a major impact when you're doing processing.
Okay, I'll move away from AWS questions, but there are more. Can you share any additional information regarding the PTP, the PTP iDevice? Yeah, I'm reading that correctly.
Yeah, the Raspberry Pi with GPS antenna. Well, it's the same thing we had with the Lockdown Rock project, and it's a Raspberry Pi where an additional board is placed on top to connect the GPS antenna, and then it's running a Grandmaster service which gets the GPS synchronized timestamping out. And of course, this is not highest quality because the Raspberry Pi does not support hardware timestamping. So it's a workaround, but it's a fairly comparably cheap workaround, and yeah, for this purpose, it served as well.
Okay. There's someone here saying they're running RAVENNA virtual sound card. If they had that and a PTP clock, could they receive the stream?
So receive the stream that we are transmitting right now, I guess. So connecting to the AWS. If you are as a viewer of this webinar want to try SRT, and you have actually a GPS synced PTP master, yes, we can exchange after that, because those are limited resources, very limited resources. So I will not open them to anybody, but you can send emails and we can discuss that. And I think it will benefit the whole community of having more people trying to test it and to check that the infrastructure is stable enough.
Yeah, so to be clear, the AS67 sound card would need to have an access point or a TX, which is offering the AS67 stream. So that's where the gateway function comes into a game again. So you would have to set up the gateway, which would package or unpack the AS67 stream into the SRT connecting to the Amazon Web Services Cloud.
Okay, thank you. What size buffers do you recommend? Also, doesn't the SRT receivers buffer accommodate for jitter and latency in such a way that audio receivers don't perceive that latency?
So SRT doesn't see the audio. SRT doesn't see the RTP stream. SRT has its own latency mechanism. And so the receiver needs to deal with the SRT delay and the network delay and all the delays that are at stake. So how to do that? Well, that's a good question. Right now it's try and error, but I wish we had some way of computing. Well, actually, some devices have. So we saw that on the Prodigy, for instance, you can see the stream delay. So this is how you actually infer the size of the receiver.
Yeah, let me just add to this, because I think the question behind the question is actually, would you actually need a large receiver buffer, just like the numbers indicate in your web page, or is there some, sort of constant delay which you don't have to have the buffer size available for? That depends actually on how large the jitter overall is, including the SRT process. Of course, any delay which is statically or which is always there does not have to be in the buffers themselves. That's part of how Ravenna devices actually work. You dial in a latency, but that doesn't mean that you have to have the full buffer size for that particular latency if a large part of that transport latency is static anyway. So the buffers only have to account for the packet jitter. But since the SRT is doing this retransmission request, there's quite a lot or large amount of jitter contributing to the also used buffers in the devices. And that's where Ravenna devices usually have a big benefit.
And the delay on the web page, the delay is a mean over tenths of a second, so over 5,000 packets, give or take. So this is why it is pretty stable, I assure you. And again, in the InCloudView screenshot, we would see that there was between the minimum and the maximum packet arrival time, there was around 2,000 samples. So because the internet is in between, you will get a jitter of 20, 30 milliseconds, something like that. Anyway.
Okay, next question. They can see the commercial equipment that's being used, but they can't find information about the PTP iDevice with GPS. Can you point to some more information about that device that's used in the direct out setup?
Sorry, you mean the Raspberry Pi again, or?
Okay, so that's what it is. So is the Grandmaster GPS device, that's the Raspberry Pi, yeah?
Yeah.
Yes.
Okay, fine. Okay. And somebody else has asked if there's any details on the Raspberry Pi PTP setup.
Yeah, Claudio, you need to share this information, because it's I cannot find it on the internet anyway. So you have to share a link at some point.
There's no link.
Maybe it's from Claudio's garage. I don't know. It's another supplier. I don't know.
It's in his brain.
If you want to know more about this, of course you can contact us directly, and we are happy to help.
Okay, all right, that's great. So just someone's asking, so you made unicast stream with SRT, yeah?
That's a question.
Yes.
So SRT is actually only transporting the RTP layer. So this is layer 5, I guess. So it's not about unicast or multicast. And when you receive on the receiver side, you get back your layer 5, and you have to reconstruct your IP packet with layer 3 and 4. So layer 3 being the IP address, and layer 4 being the UDP layer. So on the receiving side, you actually choose the new address, which may be unicast or multicast, and the new port, which may be 5004 or whatever you want. And this is one of the, this is why I try to make some kind of gateway software to ease the configuration of that, because otherwise you get only command lines and trying to configure, etc. So it's the challenge is here. The challenge is to transport the metadata around the stream and to accommodate to the translation of this metadata given the local infrastructure, which may not have the same multicast addressing, the same, etc. And including the QoS, of course, because the QoS might not be the same, and etc. etc.
Okay, all right. You mentioned the AWS time sync service. Why and how is that involved with your system?
Well, I can jump in here, and then Angela can provide more information. But Crony is their synchronization system that AWS uses, and basically it's just another implementation of network time protocol. So it's nothing. It's just a method for which they synchronize their equipment to the network time and GPS. Simply another implementation.
Yeah, so it's not showing here, of course, because this is not the idea. But I think one of the benefits of the cloud is you can have processing in the cloud, and you can, for example, take this stream that we send into the cloud and have a module somewhere that can process that and then send it back to another system. And for that processing, you want to have also synchronization, right? And that's when you use Crony. And especially if you have some processing in the cloud, and because you need to have your module synchronized to your source or to your receiver. And that's why you need the GPS OA to synchronize that. And that's what Crony is going to give you.
So they wouldn't, strictly spoken, they wouldn't have been needed for this demonstration, right?
No, not for this demo. Not
No.
for this demo, because we're doing a direct connection between the two servers. Yeah.
Yeah.
So actually, I am kind of using the global time to deduct the delay on the web page. So it is using the time of the server, but it is not using any synchronization service. The time provided by the default Amazon service is enough for this kind of time.
Yeah, exactly, yeah.
Okay, there's so many more questions. We're not going to get through them. So I think, and we come up to the hour, so I think we'll just do one last question, which is obviously, other than the Ravenna audio equipment itself, how much did this cost in terms of equipment? What if we want to do this ourselves? How much is this going to cost us?
It all depends on the equipment you want to use and what you want to transmit. If you want to transmit only to channels, there are a few choices, many Ravenna partners that can provide that. If you need something a little bit more sophisticated or with more channels and more processing, then you have to talk to each specific partner. It's hard to say how much that is. It all depends on your application.
Yeah, I think Angela also.
I'm not sure if it was a fair answer, but
well, Angela, I think it's also the overall cost of the solution, right? So there's also the AWS service fees, right? So that, you know, and those depending on how much traffic you're sending can be significant, but you know, audio is pretty good, right? If you're sending video and other things, it could get really expensive.
Yeah, and on top of that, there's a lot of time. So if you want to do that yourself, like DIY style, you can begin with a Raspberry Pi, and if Claudio gives us enough information, it can ask as a PTP Grandmaster, or you buy your PTP Grandmaster. So the only thing that you need to do that is a GPS PTP Grandmaster, and they can go down to, I have seen down to $1,500. But you need that for sure. Then you need a device that will act as a gateway, and this is why it gets tricky, because you need to be pretty geeky to make it work. I mean, it's simple, and yet it requires a lot of knowledge. So again, if you want to test it, we can discuss, and I'm happy to share, and I'm sure my colleagues here will too. But the point is rather for us as companies to offer the service of transporting the audio and processing the audio rather than just letting you, the customer, build the solution. Okay, well, look, that's great. We've had our hour. There are more questions, so we'll talk about how to get the other answers out. A great presentation and an industry first, so I'll hand back to Andreas.
Yes, sure. Okay, so thanks everyone for participating here, to Angelo, Bill, Niklas, and Claudio for helping putting this presentation and this demonstration together. More answers, as always, are available on the Ravenna website. We have the special remote production website arranged for you guys, where the live demonstration will be alive for another few days at least. And more resources are on other parts of the Ravenna network available. That's it for today. As I said at the beginning, it's the final presentation of the remote session series. If you have any questions regarding this presentation or any of the previous presentations or anything else, just shoot an email to ravenna@alcnetworks.de, or you can find contact addresses of the participating partners on their websites, of course, as well. I'm happy to forward anything which relates to merging direct out or ROS, of course. And yeah, since we are very close to the holiday season, I'd like to wish all of you a happy holidays. Stay safe, enjoy the calm time, which will be a bit calmer than usually, at least here in Germany. And I hope to see every one of you back next year when we are starting our next activity. So stay tuned. Thank you for joining in and enjoy the rest of your day. Thank you very much.
Thank you.
Thanks, Andreas.
Thank you. Happy holidays. Thank you.
Thank you.
Happy holidays.
Happy holidays, everyone.
Happy holidays.